Good morning. Today I will present you some things about packaging and bonding. I'm from Finetech. My name is Sylvain Dulphy, and let's speak about specificities for quantum. Half an hour is short. There will be some questions at the end of the session, so reserve your question. I'm trying to make it understandable, but So who is Finetech? We are a German-based in Berlin company, family-owned, and we are specialized in bonding techniques. Since 30 years, we do bonding technologies and bonding machines. That's what we do, and this is our purpose from the beginning. So we are really a pure player. We have a lot of experience on the different development in the technologies in the years. And as you already see, we have easy R&D and tabletop machine up to full automatic machines. One of the particularities is that we are fully integrated, which means that the machine is our design, the system is our design, the software is our design. We do the production ourselves. And we have, of course, application services. There's nothing, even though bonding is known since a long time, everything's particular, and every topic, every project needs to have some support on how to do. You usually, guys, do the design of the parts. You imagine how it could be bonded, but the way to do it, and we will go through these details, are very particular to each of your products. And the last part, we are based in Berlin, headquarters, with everyone designing the parts. But we are also a worldwide company doing services in every continent. We have 2 locations in the US, including a clean room. We have also a location in China, with a clean room also for demo. And we have service based in Bangkok for Southeast Asia and in Japan. And of course, Europe being served from Berlin with the service, with the production, with the application support, and a big clean room with all the machines. So today's subject, packaging for quantum. So we are doing bonding. So packaging is a wide area, really wide. We will focus on the bonding part of the packaging, so after the wafer fab. On the quantum, even though we are not experts of quantum, our customers are. And what we find out is that there are several hardware devices and hardware components. We are focused on the hardware because today, software, application, any kind of algorithm cannot work without hardware. And it's even now a pair of an algorithm with a specific hardware. So it's very important to make the hardware work. And there's a few companies now in quantum, and specifically in Europe, but also in the US and in Asia, that are working on those specific devices. Very, very important devices and very specific. Main applications are here. There could be more details from those specific guys that could tell you that in each category there are so many varieties. This is what is exciting about quantum. Seems like we are reinventing things for new needs, new requests, pushing the technologies a lot. And those guys developing those devices, they are just doing new things, new hardware, new components. Let's start with quantum computing. This is an example of superconducting processor chip, quantum processor chip, that has been done by the Walter Meister Institute in Germany. Where with our machine, we could do some indium bump interconnect, which is what we see on the right. This is indium bumps. Now the indium bump size is going to 5 micron with a pitch of 10 to 15 micron. There's a lot of them on those qubits chips that are very big. It's more than 1 centimeter. So there's quite tricky things to be done here to succeed in the connections of all those indium bumps. So for quantum computing, you have the chips. you have the qubit chips on one die, one silicon die. You place it on the substrate to have the signals going out. Remember that those qubit chips go in the cryostat. No? And we found out some 10 years ago, maybe, people were saying that we could have a quantum computer with 100 qubits. And this was the dream coming in the next 10 years. And then by the time they developed the thing, they found out that the uncertainty was a difficulty, and we couldn't have perfect qubits. So the going around was having more qubits and having some algorithm and some treatment afterwards. So more qubits means how many? 1,000? 10,000? Now we are jumping to 100,000 and 1 million qubits to have what they call a quantum computer. In between, there's all kind of hybrid things existing, but we are targeting now in this market the 1 million qubits. 1 million qubits in a cryostat is something huge. If you give the image from the beginning of the electronics, it was bulbs, huge room, doing one calculation, an addition. And then now it's a part of a chip. It's 1 millimeter square, even less. It will be the same thing, and technology in semiconductor allows to go faster than what we do in electronics in the past 50 years. So now we're going to stack. They are going to stack. And stacking qubits to have it compact, to have signals processing very fast, low noise, no low loss, and to be in the smallest possible cryostat. This stack is not an easy topic. It's something quite new in the industry on how to stack those things and put that in a qubit. And that's part of the thing that we are doing for those people with our machines. Other application, quantum communication, safety of the communication, safety keys, crypto, etc. These are different hardware topics, different components. What for those who have access to that, what we see is the setup of the lab. Optical table, not new, with a setup optical signals with any kind of modulators, transforming, light source, detectors. Those tables are, for those who saw that, probably 2 meters by 2 meters by 4 setups in the labs to test and to have the proof of the concept of how to deal with those things. From this, once again, we want to put that in electronics everywhere. In communication, in telecommunication, in satellites, in everywhere. So quantum people are designing new devices, new chips. So modulators, waveguides, different things to play with the light. Those are new devices. The new devices will have to be connected to each other through fiber optics, through any kind of passive optical transmission, some active. So there's all new components and how to bond them together, how to connect them together with minimum loss. And that's part of the topic they are tackling, and we are helping on the bonding part. So going from square meters to square centimeters, and there's no limit there. We know about semiconductor, how it works. We know about those technology. They will not stop there. They will go further, probably. If you think of the energy of the, going back to the cryostat, if you think of the energy to cool down to a few kelvins, those big devices, the smaller, the better, as always. And the leverage of the energy saving is so huge. There's really a lot of things to do on opticals and on compactness and assembly of those things. If I be not an expert, just seeing that from the background, those quantum parts and quantum components can be maybe separated in 3 things. The light sources, that's example of things that you can have. So laser emitter, VCSELs, yeah, we know them. They are just being used slightly different, some of them. And maybe the wavelengths are different also. But globally, we take a laser diode and we solder it somewhere. This is part of the example of things that we can do. Once you have your light source, you have to modify this light. So you have passive and active components to modify the light and to play with it. And once again, here the components are very different. So you may have some lenses. I was discussing with some people about 3D printing lenses for the signal processing. There will be some mirrors. There will be some plastic package like this yellow one on the third picture. In fact, it's a mirror with some lens for the transceiver to transmit the light from the VCSEL to the output and from the output to the inside with a photodiode detection. All those things are transforming the light, passive or active. Modulators are part of it, waveguides. And at the end, of course, as you are using light, we use a detector to detect these lights. And for quantum, we want to detect everything. Every single photon should be detected. This is this kind of accuracy that is wanting for by this market. No? So those detectors, new devices based on existing technologies, maybe not. And you can trigger those things with lasers also, etc. And the purpose is, of course, after the light, to use the existing electronics. So electrical signals, electrons, from photons to electrons. So once again, connections, optics to electric, modification, new component, new connections, and high level of accuracy. Some product example, transceivers, photodiodes, and laser source. Some example of this bonding that we can have. So on the right picture. No? So very tiny devices. VCSELs today, 150 micron by 150 micron devices is standard, 100 by 200, depending. No? And we are now speaking about micro LED as part of the optical communication for data transmission. Micro LED is one scale lower in dimension, a lot lower. Pluggables, same kind of things, with glue, with UV tacking, with different assemblies that we will go through just after. So let's go a little bit in detail. Well, to not be in detail, it's just to oversee some of the bonding techniques that we use that are standard, but maybe pushed to some limits for this quantum product and quantum components. I want to go back to first things about what is bonding and how we do it, or how the industry is doing it. It's not only Finetech. The purpose is to take a component with some bonding materials and to bond it to a substrate. Electrical signals, most of them. It could be no signals, just mechanic. It could be optical. One important tool that people forget, we need to handle those devices, whether the big qubit, several square centimeters, or whether the VCSELs. Handling tool, it's always a nightmare for everyone, even for us. Because you sell a machine with a process, and this is the big stuff. But then you need a tool. It's just like the hands. Take out your fingers. What can you do with? Not that much. You need a full training. You need to do it differently. The tool is the same thing. It's the finger. If you do the right tool, you can handle the things. You can precisely bond it. You can do the force. You can do the coplanarity. You can do the accurate placement. The die will not move, etc. So always, it's not the costly part. Sometimes it is, but it's usually not the costly part compared to the machine. But it is one of the essential parts. It's just like a finger doing things precisely. The other counterpart also is the holding plate. The holding plate with the substrate should be very flat, maybe on a big surface, because you want coplanarity for those very small indium bumps, for example. It can be heated depending on the process that you need. The heat distribution should be even and should go to the right place on top of the substrate. So there's all kinds of bonding techniques. So those things are things that we deal with every day. And they are the one that makes it efficient, that makes the process being efficient. Bonding is the process to stick them together and make them stay and have this optical, electrical, mechanical connection. All of them, part of them, two of them, one of them, depending on the device and depending on the components. Huh? So always think about that. Huh? Doing some bonding is one thing. Developing indium bumps and the process is one thing. Don't forget the handling. Don't forget the environment. Otherwise, might not succeed. So some basic reflow, autolytic solder. Solder in PCB-A is been done since 70 years, 100, 2000. No, maybe not. Almost or something. Yeah. So purpose, you could have some layers, you could have some foils, you could have some bumps. There's different materials. Indium is one of them for the Cryostar. Sax 305 is another well-known one. Leaded, not leaded, antimony. There's a lot of alloys being there. The purpose here is to heat and maybe control the force or put some force depending on what you do. Control the force because the solder alloy will melt. When it is melted, then there's no force. If you don't control the force, you just scrap everything down. So you have to control the force when you are doing the bonding. And the same thing, you have to control the heat from the bottom, from the top, very precisely, specifically for those big devices with so many balls or contacts. We also saw some, in quantum, we also saw some soldering which are surface, indium surfaces, just to make it cool down, to make the qubit cool down and have the best cooling possibilities from the qubit itself or for the processor. So what do we do? It's example of laser diode on submount. This is traditional things that we do since more than 20 years already with our machines. First step, so laser diode from silicon on submount. And then you take this subassembly, this module, and you put that in a package. Several of them, maybe, or with an ASIC, or with some optical functions, or just several lasers with several wavelengths, and some optical components to go out. Here, for this example, the solder is very important for this cooling down. The overhang is very important for the laser diode, not for the emitting part, so that it is not polluted and that you have the best quality of the light going out. And the best solder you have, the less cracks, the less void, the better cooling possibility, the better power you have, and the better reliability you have on the product. Thermocompression. Thermocompression. Put some thermal, some heat, and control the pressure on the two devices. Here, depending on the count, depending on the number of bumps, depending on what you do, you could need high force. Imagine those big qubits, 2 centimeter by 2 centimeter with indium bumps, 10 micron, and you have thousands of them, more than that. The amount of force per bump is very low, really very low. But if you multiply by 10,000, 100,000, then the force is going way over 100 Newton. So having a machine able to control the force, still keeping the accuracy, still keeping the coplanarity with the correct tool is definitely a challenge and something to be looked at every time you want to do that. So example, stacking with indium bumps for the Cryostar applications, or gold to gold, copper to copper. Copper to copper is known already in the industry for hybrid bonding, for those memories thing that TSMC and some others do. So you align, you bond together with thermocompression, and then you go to the oven to annealing 300-degree process so that the copper bonds grow and connect to each other. This is standard hybrid connection working, but there's a lot more with 3.526 products to silicon where this cannot work with the 300 degrees annealing because thermal coefficients, dilatation between products are very, very different. Then you have to do it differently. So, example of thermocompression, yeah, and result that you can have. So part of what in the generic hybrid bonding, we could call it heterogeneous bonding. So those 3.5 or 2.6 products to silicon to make sure that you have the accurate placement and bonding, and that you don't lose them due to a certain time exposed to temperature, we try to do it cold. Cold is less than 80 degrees, let's say that. So you need to activate the surface, sometimes clean from oxide, from metal pollution, the different contact, and then do the bonding. What we do in our machine now, we have those tools, we have this accurate placement. What we do now is also having this plasma cleaning. Why plasma cleaning? If you use indium, it does have oxide issues in normal atmosphere, in standard atmosphere. So you need to clean that. The standard cleaning methodologies are formic acid. Formic acid is a certain 30 seconds, maybe more process. It has some heat, and it does jeopardize the accuracy of the placement. So we are trying now with some customers to replace that by a plasma local treatment of the dyes and the substrate on the contact and do this thermocompression. Ultrasonic. So ultrasonic is well known for the wire bondings, which we don't do. We do everything about bonding except wire bonding. It is also a known technology for just bonding dyes. You have some bumps, and you have this transducer in a fraction of a second doing this very active movement, very small movement. The friction puts some heat, enough heat to have this local melting of the bumps and doing the solder. It is really efficient. We can do that very fast, and it can be 4 micron accurate in post-bonding accuracy. This is quite challenging, depending on the product, depending on the tool. But this is something that is working and can be fast. I think we have a short video here. Typically things we do in the machine. So placing small devices. We don't see the movement here, but there's a movement and there's a bonding. Adhesive bonding, known. So you put some epoxy glue, whether conductive or not, depending on your product. And once again, we are tackling here accurate placement. So to make it happen and not moving the device up to the oven with a risk of moving the parts together or having the parts move because of the curing of the glue that is pulling one side or the other, UV tacking is definitely a good thing. So we dispense the glue, we place the device, we control the bond line thickness and the accuracy, and then we have an immediate UV tacking to fix the position. And then you can do the 45 minutes curing in the oven. The classical things would be for UV, for VCSEL and photodiodes, vertical components on a substrate with some glue dispensed between. But there's also side-by-side topics. Component to component, passive to passive, electrical, but also with fibers. So the big topic in the industry is this optical alignment today. This is what works today. It is a nightmare for everyone because it takes so long time to do each alignment, and it does cost. So the industry is now working a lot on in-between devices that would be passive, that would do this alignment of with low loss, and to do passive alignment and just die bonding and those polymer, whatever, bonding. It's coming very soon. And this is a real difference for the market to go to scale up. Once again, target, pluggables, data centers, data transmissions, AI. This is just the thing of today. So this is the thing where there are volumes, huge volumes. Another technique that we've been developing that is working very fine. Due to this heterogeneous bonding, we have this thermal coefficient expansion between 3, 5, 2, 6 materials and silicon. So one way is not to heat the full thing. So if we can go through the substrate, so through the silicon, and heat just locally, we can do a fast bonding. Laser is a perfect candidate for that. really high power, really focused, and you can just hit the bonding part for 1 second or a few seconds, and you have a bonding done properly. There's different wavelengths, different techniques of doing it, depending on the device you want to bond, depending on the thickness of the substrate, depending on whether it is a certain surface or just this 200 micron thing. So we have two or three laser wavelength source now compatible with the machine, and to do that. So we align the parts and we do the bonding through that. Yeah. And this is one of the examples of things that are working since already more than 1 year at our partner Fix in Netherlands. They have our machine here on the right. So they pick up VCSELs and photodiodes. They put that on a wafer, so it's a die-to-wafer assembly. And as soon as it is there, we shoot the laser from the bottom, and the solder is done. So it's a fast process. It's solder. Remember that solder profile usually is 1 minute 30? Here we're doing 2 seconds. Yeah, okay. So this is a summary of what you can see in our machines. So it's automatic machines, modular, versatile. There's different modules for the process. So all those processes that you've seen, we can install the module. So the laser, the thermal compression, the soldering, the dispense. You install the module in the machine, and then the setup is there. And then you can jump from one process to another process, from one batch of product to another batch of product. Having the different process being done in the same machine with a switchover, which is equivalent from one production to the other, which is equivalent just to unload the trays, the wafer, the gel packs. So this is a UV head, so placement head with UV tacking that we will see. Just like for transceiver here, and the UV tacking. Yeah. Yep, done. This is a summary of available techniques and bonding techniques today. Doesn't mean that there's not other ones. Doesn't mean that there's no declination of some of them, because each line is maybe a project by itself for some of the assembly. And that's what we propose. Every time we sell a machine, we start to evaluate the bonding capacity, to evaluate the process part with the customer. So we do test in our clean room with all our customers to test what they want to do with their specificities of the product, whether it is a big one, a small one in the cavity, stacking, and maybe we test and we compare different bonding processes. And so I was just checking the time. It's half an hour. Presentation is done.